For this video, we are going to review the material presented in Unit 4, which is Chapter 7 and 8, to better prepare you for your last test, which is the Unit 4 test. It is called the final exam, but it's not really a true final exam because it's not cumulative. It's just the information in Chapter 7 and 8. And I'm going to start with the free response questions first in the review, and then I'll move on to the multiple choice. So question number 9 says a random sample of 9 TI-89 calculators being sold on the internet has the following prices in dollars. So this is the distribution of the prices. Assume the population standard deviation is sigma equals 35 and that the population is approximately normal. Construct a 90% confidence interval for the mean price of all TI-89s being sold over the internet. So we know that the problem wants us to construct a confidence interval, and if we recall from chapter 7, a confidence interval is comprised of a point estimate plus or minus a margin of error. And when we looked at this, we wrote two different types of confidence intervals. It was either the X bar, which is estimating the population mean, plus or minus our critical value, which is a z-score, if we know the value of sigma, and then the standard deviation of X bar, or we have X bar plus or minus the critical value for a t interval and the standard deviation of X bar, where the standard error of X bar, where the standard error is actually sigma divided by the square root of n for a z interval, or it's s divided by the square root of n for a t interval. So we have to ask ourselves, is sigma known? Do we know the value of sigma? And since we do know the value of sigma, that means we will construct a z interval here. So we need to be able to find what is the sample mean if I were to add all these values together, and then we want to find our critical value. And then we also want to be able to find this, which is the standard error of X bar. So our 90% confidence interval, this will help us find our critical value for z. We know that it's 90%, so we have to figure out what is the area that remains in the tail. In this case, we have 5% on each side. We know that 90% plus 5 and 5 is 100%. So if we actually look at our table here, so if I go to my table E and I want to find the number closest to 5%, 0.05, which would be this one, negative 1.65, and so we know for our confidence interval that it would be the critical value will be plus or minus 1.65, but we just use positive 1.65 because of the plus or minus is already in the formula. So now we want to find the average. The average is going to be the sum of all these numbers divided by 9, and so we get 145.56. And now we can set up our confidence interval formula. So 145.6 plus or minus our critical value, 1.65, times the standard deviation, which is 35, divided by the square root of 9. And we have two values. So if we subtract in our formula, we get 126.31, which is the kind of the lower bound of our confidence interval. That's the price. That's the lowest average for the population we expect. And the highest average that we expect is $164.81. And then we can write our little summary. We are 90% confident the true mean cost for all TI-89s being sold on the internet is between $126.31 and $164.81. If we know sigma, we can construct a z interval. So that's we were able to construct a z interval, so using table E to find the critical value versus using table F because this is known. So let's look at another example, number 10, in which we don't know the population standard deviation. So in this example, we want to ask ourselves, is sigma known? So it tells us in this problem here that boxes of raisins are labeled as 22 ounces. Following are the weights in ounces of a sample of 12 boxes. Is it reasonable to assume that the population, or it is reasonable to assume that the population is approximately normal. So the standard deviation is unknown. Nowhere in the problem, like in this one, it said sigma equals this. So that means this value is unknown, and because it's unknown, I need to find a t-interval, which is going to use table F. So we're going to want to be able to find the sample mean like before. We want to be able to find the sample standard deviation, and we want to be able to find the critical value using table F. And so we know we have to use table F solely because of this, because this is unknown. And in this problem, we use table E because this was known. So if I add all these ounces together and divide by 12, I'll get 22.07 ounces. And then we know that the formula we talked about before, this is for variance. And then if I take the square root of this, that'll be the standard deviation. So the standard deviation is 0.0186 ounces. And we want to construct a 90% confidence interval. That means we need to find degrees of freedom, and we need to be able to look at table F for this information. So our degrees of freedom is sample size minus 1. So 12 boxes minus 1 would be 11. So if I go to table F, and now I look at the confidence interval portion, we want a 90% confidence interval, and it was 11. So 1.796 would be my critical value for this confidence interval. So when I return back to the problem, that's going to be my t-value. And then we can set it up. 22.07, which is my point estimate, plus or minus my critical value, times the standard error of the point estimate. And then we look at, well, what is our interval? Let me go back here. I went too fast. So from 21.97 ounces to 22.17 ounces is what we're estimating the true mean to be for all boxes of raisins. And then we can kind of summarize that. We are 98% confident that the true mean weight of all boxes of raisins is between 21.97 ounces and 22.17 ounces. So those are kind of like a little review of confidence intervals that we talked about in chapter 7, beginning of unit 4. And then we'll switch gears and look at hypothesis testing, which we just finished talking about. So 8.2, and we'll look at an example from 8.3 as well. It says the average greyhound can reach a top speed of 18.9 meters per second. A particular greyhound breeder claims her dogs are faster than the average greyhound. A sample of 30 of her dogs ran, on average, 19.2 meters per second with a population standard deviation of 1.2 meters per second. With alpha equals 0.05, use the traditional method to test the validity of her claim. So you're being told more or less which method to use, the traditional method. So we know that we need to, one, identify the key information in the problem. We know the population average. We need to be able to find the sample mean. We need to be able to find the sample size. We need to be able to find alpha, and we need to be able to find sigma. If we're using the traditional method for a z-test. So in the problem, they give us the value of sigma, population standard deviation, and so we know that we're going to be able to use a z-test here. So my population average, 18.9, sample size is 30, and then we know that the sample mean is 19.2, alpha is 0.05, and we know the standard deviation of the population is 1.2. So we can use the z-test, and that means we'll be looking up table E for our critical value. First step, state the hypotheses. Our null hypothesis is that the average speeds are no different. The average speed for her greyhounds and the national greyhounds are no different. So we say that the true average speed for her greyhounds are 18.9 meters per second. And then the alternative hypothesis is that she really thinks her greyhounds are faster than the average greyhound. So we would use greater than 18.9. And this would be our claim because it's not stated otherwise in the problem. And then we look at, well, what is our, correction, it does say, claims her dogs are faster than average. So this would still be our claim because even though it is stated, it's the alternative. And generally the alternative hypothesis is the claim regardless, unless it's stated otherwise in the problem. This one actually states claims, but it's claiming what her assumption is. So our critical value because this is a z-test, comes from table E, and we have to be able to know how to use alpha in this sense for this traditional method test. So a critical value, table E, we look at alpha as 0.05. When I drop my distribution, because it is a right-tailed test, the entire area of alpha is in the right tail, 0.05. And then we know that we need to consult table E, which means I really want the area to the left. And left of that would be 0.95. So when I go to table E here, we could look up 0.05, which we already did previously. So it's negative 1.65. But hopefully that will send up a red flag because we are looking at a right tail test. And if I go to 0.95, here, it's positive 1.65. And I'll use this as my critical value. It's very necessary to find the correct critical value because that's going to affect our decision if we do not find the correct critical value. So now that I have the critical value, we want to find the test value. So we just find the z-score based on the data from the information provided in the problem. So sample mean minus population mean divided by standard deviation of the population, which is divided by the square root of the sample size, and the critical value we get is 1.37. I'll look at, well, in relation to my distribution here, to my critical value, the 1.37 is not inside the critical region, it's on the outside of the critical region. So that our decision would be not to reject the null hypothesis. And that's because the 1.37 is not inside the critical region. So when I write my little statement now, there is not sufficient evidence to support her claim. So hopefully that makes sense. Because we are deciding not to reject the null hypothesis, that means her claim cannot be supported. Her greyhounds are no faster than the average greyhound. They essentially have the same speed in meters per second, even though on average hers might have ran a little faster. Essentially, or statistically, it's more or less the same speed. They're not that fast. Let's look at another hypothesis test here, see if we can use the p-value method now. So for number 12 in the review, it says a recent study indicated that the average amount spent for breakfast by business managers was 7.58 with a standard deviation of 42 cents. It was felt that breakfasts on the West Coast were higher than 7.58 or $7.58. A sample of 81 business managers on the West Coast had an average breakfast cost of $7.65 with alpha equals 0.10. Use the p-value method to determine if it can be supported that breakfasts were higher than $7.58 on the West Coast. So for that, we know that we need to identify this pieces of information. We want to make sure we can identify these 5 things, and I've already pre-wrote sigma because it tells us in the problem that we have the population standard deviation. So in this first sentence, a recent survey indicated that the average amount of breakfast for business managers was $7.58. Well, that's the population value with a standard deviation of 42 cents. This value is connected to the 758. This is the population average. That means this has to be a population standard deviation. I know that those two things are connected. And then we know that the sample size is 81. We also know that the average for the sample mean based on the 81 business managers was $7.65, and then alpha was 0.10. And we want to be able to utilize the p-value method. So first step is the same as before. What is a null and the alternative hypothesis? In this case, we're stating that the average cost of breakfast for the sample business managers is essentially no different than the average cost of just business managers in general. So the true average cost of business breakfast, too many B's, is no different than $7.58. Whereas alternatively, we feel like that they've paid less than that amount or more than that amount. It says higher than. It was felt that the breakfasts on the West Coast were higher than that amount. So we would use greater than, and that would be our claim. since we are doing the p-value method, that means instead of us finding the critical value, we're actually going to find the test value. So the test value would be the z-score. So here's our z-score formula. Substitute in all the appropriate values, and when we evaluate this, we get 1.5 for the z-score. This is crucial because now the p-value that we find is going to be based on this z-score value. So when I draw up my distribution, I have a z-score of 1.50, and I'm interested in the area to the left because this is the probability value based on this z-score because it's a right-tailed test. So when we go to our distribution, I want to go to 1.50, which is 0.9332, which is clearly not the area that was shaded in. Doesn't look like I colored in more than 90% of the distribution, so that must be the area to the right. And then I can take that area and I can subtract it from 1 to get this number. So this is my p-value. My p-value is 0.0668, and we have to remember when we're using the p-value, we look at two situations. Is the p-value less than or equal to alpha, or is the p-value greater than alpha? If it's less than alpha, if it's the first situation, then we are going to reject the null hypothesis. If it's the second situation, then we are not going to reject the null hypothesis. In this case, the p-value was less than alpha, which is 0.10. So we will be rejecting the null hypothesis, and then we can state in our summary, there is sufficient evidence to support the claim. And I'm just keeping this summary part short and sweet because there's a lot of questions I want to make sure I get through, and I don't want to make the video too long for you. Now, let's say that we really didn't want to find the p-value and we wanted to do like the traditional method. So if I were to find the critical value for this, using the same alpha value, then that critical value will be 1.28. And now if I kind of compare it, so my critical value was 1.28 and the test value that we already found was 1.50, we would still reject based on the traditional method. So whatever decision we make for the p-value method should be the same decision you make using the traditional method. So in essence, it doesn't quite matter if you use the p-value or the traditional method because you'll get the same outcome. You should get the same outcome. If one method causes you to reject and another method causes you not to reject, then we would need to reevaluate, make sure we didn't make any errors in our calculation because we should get the same outcome each time. All right, let's do one more example for hypothesis testing, and then we'll go through the multiple choice questions. So for number 13, it says Reginald Brown, an inspector for the Department of Weights and Measures, weighed 15 18-ounce boxes of cereals of cornflakes. He found that their mean weight to be 17.8 ounces with the standard deviation of 0.04 ounces. At alpha equals 0.01, are the cereal boxes lighter than they should be? So for this particular problem, again, we look at, what information do we need to be able to find? So these are more or less the 5 things that we look at. Now in the problem, if we notice, well, the wording at least, so the particular gentleman at the Department of Weights and Measures, so that may not be a real department, but he weighed 15 18-ounce boxes of cereals, so that's the sample size. And from those 15 boxes of cereals, he found their weight to be 17.8 ounces, so that's the sample mean, with a standard deviation of 0.04. So these two numbers are based on the sample data. That means this 0.4 is the sample standard deviation. So that's my S value, that 0.04. That means that this is going to be a t-test for hypothesis testing. Still, step 1's the same. State our hypotheses. The null hypothesis, there is no difference in the average. So essentially, the true mean weight for the boxes of cereal is 18 ounces. And then alternatively, they felt like that the boxes were lighter. Are the cereal boxes lighter than they should be? Well, then is the true mean really less than 18 boxes, right? We're being told that each box contains 18 ounces of cereal or cornflakes, but are the boxes really lighter than they should be? And that particular statement is our claim. And then we look at, since we're doing the t-test, this is like the traditional method. So in this case, we want to find our critical value, which is going to come from table F. So we got to find degrees of freedom. We know this is a one-tailed test because of the symbol, the less than symbol in the problem. Degrees of freedom, 15 minus 1 is 14. And if I go to my table now and I look at, so I'll switch back and forth. We have 14 degrees of freedom, and we want the alpha was 0.01. So it was a one-tailed test, 0.01. Here we go. Find up where they meet. So this is my critical value here, 2.624. And then make sure that we will end up using the negative value because it's a right-tailed test. But then for the third step, we want to find our test value. Right, so we use the t-test formula, like a t-score, evaluate that, and we end up getting negative 1.94. And then we determine, based on this distribution here and based on the test value, if the test value is on the inside of the critical region, then we reject. If the test value is on the outside of the critical region, then we do not reject. So in this case, our decision is not to reject the null hypothesis, since that test value of negative 1.94 is not inside the critical region. And so we can safely state that there is not sufficient evidence to support this particular claim. So now we'll run through the multiple choice questions, and those should be a little fairly quicker. Those are just more so to quickly check some understanding, as opposed to the non-multiple choice questions, which carries out a great deal of the content presented in Unit 4. So this particular question comes from Chapter 7. It says, identify the degree of confidence displayed in the confidence interval shown below. So essentially, what type of confidence interval is this? And when we look at that question, we have to think about, well, what would be the area in the middle of the distribution? If you have 5% here and 5% here, then what area is really left in the middle of our distribution? So that would be 90%. So this would be a 90% confidence interval. So that would be the gist of question number 1. And then question number 2 is simply asking us to interpret. Right? So a sample of 37 light bulbs had a mean life of 594 hours. A 95% confidence interval for the population mean was this, 588.5 all the way to 599.5. Which of the following statements is a correct interpretation? Well, every time we interpreted it in the Chapter 7 videos, and then now in the test review videos, it's always we are blank % confident, and then we talk about what the interval represents and then what the values are. So the only one that states that is C. We are 95% confident that the mean lifetime of all bulbs in the population is between those two numbers. So more or less, that's just to get you multiple choice questions are hopefully to kind of help guide you through the free response questions, because they are, they're connected to each other. For number 3, it says when should the t-distribution be used to find a confidence interval for a mean? Well, the t-distribution is only used when sigma is unknown. That's the only time we use the t-distribution, which is table F. So that's table F, and table E is when sigma is known. So anytime in the problem, if there is nowhere stated that you have a population mean or you're missing that notation sigma, then is a clear indication that we would use table F instead of table E. And then for our next question, it says determine whether the alternative hypothesis is left-tailed, right-tailed, or two-tailed. So to even determine that, we look at the alternative hypothesis. That tells us what type of test we're doing. In this case, it's not equal to, so that means a two-tailed test, because we're not really sure if the result is more or less. So we look at both ends of the spectrum. So that, in a gist, is a two-tailed test. And then question number 5, we look at, it says decide whether the null hypothesis should be rejected when alpha equals 0.01 and the p-value is 0.1112. So again, our two conditions we look at, is the p-value less than alpha or is the p-value greater than alpha? If it's less than alpha, then we need to reject. If it's greater than alpha, we do not reject. In this case, the alpha value, this is greater than this, right? This is 10% and this is 11.2%. So 11.2% likeliness of something happening is greater than a 10% likeliness of something happening. So we would not reject the null hypothesis in this case. Now, number 6 wants us to calculate a particular value. So let's see if we can do that. It's a recent survey of gasoline prices indicated the national average was $4.98 per gallon. The Dallas Automotive Club claimed that gasoline in Texas was significantly lower than the national average. A survey covering 10 different suburbs in Dallas found that the average price of gasoline was $3.29 per gallon, with the population standard deviation of 50.053. So it's like 5.3 cents. What critical value should be used to test the claim alpha equals 0.01? So to determine the critical value, we first need to determine is this a table E problem or is this a table F problem? So we look at, it states population standard deviation, so that gives us an indication that we'll be using table E for the critical value. So we draw out our distribution, has an area of 0.01. That means if I go to table E and I want to find the area closest to 0.01, which is this value here, 0.0099, we look at a z-score of negative 2.33. So the critical value that we would use for this one would be answer choice A, negative 2.33. And then in question 7, it says, according to A Beautiful Bride magazine, the average age of a groom is now 26.2 years. A sample of 16 prospective grooms in Chicago revealed that the average age was 26.6 years with a standard deviation of 5.3 years. What is the test value for the claim? So now we look at a test value. Before we looked at a critical value, now we look at a test value. So we'll determine the test value, and the problem is telling us a t-test. Now this particular one, because it is a test value, it really wouldn't matter if you confused the two formulas, because essentially they're the same. It's still sample mean minus population mean divided by some standard deviation, whether it's population or sample, divided by square root of n. But to just keep it correct, this is step 3 of the hypothesis test process. So it's a t-test value, a t-score essentially. Identify the appropriate information. So we know that this is the average age of a groom, 26.2 years. This is the sample average. So a sample of 16 prospective grooms from Chicago revealed that their average was 26.6 years. And we have a sample standard deviation because we're told that we have a t-test. So that information is connected. So substituting in the values into our formula, we get 0.30 as our test value. And then for our last question that we'll look at, number 8. Question 8, section 8.3 wants us to know, says what are the critical values for a two-tailed test when alpha is 0.02 and the sample size is 19. So that means we have to use table F for this. T-test is table F, sample size is 19. That means we want a degree of freedom of 18, and so we have to go to table F now. So table F, and we have a degree of freedom of 18, which is here. We have alpha is 0.02 and a two-tailed test, so 18 here, and then two-tailed test 0.02. We have 2.552 because it's a two-tailed test. That means we have two values. It's plus or minus. So the answer choice we look at here is B. And so this information is a quick review of what you'll be expected to know and understand and be able to do in your final unit 4 test for chapter 7 and 8.